Welcome for this course, and we continue the introduction part of the introduction to quantum mechanics. As I mentioned last time, chapter 1, and then we will start to review the basic concepts in quantum mechanics starting chapter 2 in some details, but we will go quickly to chapter 3 for a one-dimensional potential problem. But before that, I would like to make a remark. Again, for those of you who have not taken modern physics course, please review the quantum phenomena, that part of the modern physics, and we will not repeat a lot of this in this course. Let's continue the basic concept in quantum mechanics. As I mentioned last time, there are 4 important concepts in quantum mechanics which you should know, and you should be very familiar with these concepts. Okay, so the first one is the particle-wave duality. As I mentioned, all quantum matters have double faces, the dual characters. One character is the wave nature, another is the particle nature. Electron could get diffracted, and the electromagnetic wave is a particle. So the particle could be wave, and the wave could be particle. So the particle is the wave is the particle. Okay, so this is the most important concept in quantum mechanics. All quantum matters have 2 faces, okay? But you can only see one face at a time. You cannot see the both characters at the same time. Okay, so that's restricted to the Heisenberg uncertainty relation, which I will mention in just a moment later. The second key concept in quantum mechanics is the quantization of energy. So in all quantum systems, we have discrete energy levels that particles can occupy, which we call these quantized energy levels. You should have known this from your high school chemistry or physics. You know that in atoms and molecules and so on, the energies are quantized. And those quantum units of energy is a big discovery in the late 19th centuries and the early 20th centuries by Planck, Einstein, and Bohr, and so on. Okay, so you should review chapter 1 of this book, Discovery of the Quantized Energies in Quantum Matter. And in particular for photons, you get a unit of energy of photon, integer multiple of h times nu, where h is the Planck's constant and nu is the frequency of your light. And these 2 most important fundamental aspects of quantum mechanics will lead to the following consequences. One is the Heisenberg uncertainty relations, or uncertainty principles, which sets the uncertainty to determine the position and the uncertainty to determine the momentum of a quantum particle have fundamental limitations, which means that this delta x times delta p should be greater or equal to h power over 2, and this is so-called Heisenberg uncertainty relations, and we will derive such a relation in this course. Okay, so why is this h bar? And why is the factor of 2? Why is this relation greater than or equal to? Why is not exactly equal? Why is this not less than or equal to? Okay, and we will exactly derive these relations. But so far, it is a fundamental limitation of what we can know about quantum particles. If we know the exact position of the quantum particle, we don't know the momentum of that quantum particle, and vice versa. If we know the momentum of a quantum particle exactly, and we don't know where they are. Okay, and this is very much linked to this double phases, double dual characters of a quantum particle, meaning if we know the wave nature of a quantum matter, then we don't know this particle nature of that particle. Vice versa, if you know exactly the quantum particle nature of that quantum matter, and the wave nature is mirrored out. Okay, and this tied to this Heisenberg uncertainty relation, which we'll make formal mathematical connections later on, but this is the most important fundamental limitations of quantum mechanics and what we can know about the particles in the quantum limit. And the fourth important concept is the probability interpretation of this wave functions. And as I mentioned, this particle wave duality aspect, all quantum matter is associated with a wavelength, so-called diploid matter wave. And the wavelength of the diploid matter wave is equal to the Planck constant divided by the momentum of the quantum particle, and every quantum particle is associated with a matter wave. And that wave obeys Schrödinger's equation called the Schrödinger wave function. And because of this Heisenberg uncertainty relation, also the particle wave duality, all this matter wave or the wave function which describes this quantum particle shows some uncertainty when we interpret this quantum particle, and we should use a probability to interpret this matter wave, meaning we will derive such a relation. The probability to find a quantum particle is proportional to the square magnitude, the magnitude square of this wave function, or the Schrödinger wave function. I believe most of you have already noticed this, but again, this probability interpretation is necessary in quantum mechanics because precisely of these two facts, the particle wave duality and the Heisenberg uncertainty relations, which limit our knowledge to know all aspects of quantum matter, and we need to interpret those, say, experiments in the quantum region in terms of the probability distribution of the Schrödinger wave function. Okay, the necessity to apply such a probability interpretation will become clear later. By this point, you should know that the probability interpretation is kind of a consequence of this, this particle wave duality and Heisenberg uncertainty relation, and this is a fundamental limitation of what we can say about quantum matter. Okay, so if we don't apply the probability interpretation, then we cannot describe very well all these quantum experiments and understand these quantum aspects of a particle wave duality. So this great physicist in the late 19th century, in the early 20th centuries, help us to understand, to make sense out of all this kind of a seemingly contradicting experiments, and we should interpret the wave function in terms of a probability distribution. And we will derive the Schrödinger equation, which all this single particle in the quantum region should obey. Right, so we will derive such Schrödinger equations later on, but we will go very quickly because most of you have learned this in the modern physics course. So this number 3 and number 4 concepts altogether, we will be able to understand this quantum tunneling phenomena and all this very strange phenomena that classical mechanics does not have. So based on this Schrödinger picture, we could also use a more mathematical and abstract approach to reformulate this Schrödinger equation and this sort of eigenstate, eigenvalue equations to describe these quantum states, which is the eigenstates of a Hamiltonian operator, where this Hamiltonian operator stands for the quantum mechanical operator for this system energy. The total energy of the system in quantum mechanics is described by an operator called Hamiltonian. The Hamiltonian operator when you act onto the eigenstates, which leads to the eigenenergy of the system and times this eigenfunction itself. And this is called eigenvalue equation for the Hamiltonian, and this eigenvalue equation describes precisely the eigenstates or energy levels of your quantum system. For example, this ground state energy and the first excited state, and so on and so forth. And each eigenstate is associated with the eigenfunction. Okay, so we will learn how to get those eigenstates from these eigenvalue equations by solving the Schrödinger equation over there. All right, so all these important components in quantum mechanics are connected. And you could use more mathematical and abstract manner to describe such a quantum states in the Dirac notation. So Dirac-Cat state or Dirac-Bar state. And the Dirac made important contributions in quantum mechanics by introducing this more abstract mathematical formulations in terms of this linear algebra. We could make this quantum states a more abstract way so that we could project this Dirac state onto all different eigenbases. Okay, for example, we could project this Dirac states to this position eigenbasis. Then we get the Schrödinger wave function in real space. And we could also project this quantum state or Dirac state to this momentum eigenbasis. Then we get momentum eigenstate wave function, which described the probability distributions of a quantum particle in momentum space. Okay, so there is a one-to-one correspondence between the real space and momentum space wave function. It's called Fourier transform. And we will introduce such a relation between the real space and momentum space wave function. And this Heisenberg uncertainty relations could be understood in terms of this transformation between the real space and momentum space wave function. Okay, so you will learn this correspondence by explicitly studying this Fourier transformations between these two kinds of wave functions, and this we can define such uncertainty, which is the width of this wave packet in real space and also in momentum space. And you will find that this uncertainty or error bar in determining the real space location or momentum space momentum variables of quantum particle. When you make a product, this product is always greater than or equal to h bar over 2, which is kind of a proof of this Heisenberg uncertainty relation. And we could construct a more sophisticated quantum mechanical results. For example, the angular momentum. For example, the hydrogen atom. For example, simple harmonic oscillation in quantum mechanics. For example, spin. So the Schrödinger plus Dirac formulations allows us to study all kinds of quantum mechanical systems, such as the spin and orbital angular momentum and hydrogen atom, and also harmonic oscillator problem. Okay, and this is probably the outline of this course. In the very beginning, I will sort of very quickly review these four important concepts, but the last part is the main focus of our course, which will be more mathematical oriented. So we applied Schrödinger equation and Schrödinger wave function and Dirac notation and tried to more systematically study this quantum mechanical system, such as potential problem in one dimension, and such as all this subjects that I just listed, and we will go beyond this physical systems by introducing this perturbation theory, time dependent, time independent, in order to analyze the system where you have a small external potential and then you don't know how to solve this Schrödinger equation exactly, but you can make progress using perturbation theory, perturbative expansion, which is a very powerful technique in quantum physics. Okay, so that's all about this basic concepts in quantum mechanics. In case you missed anything, you should fill out the gap right away. Okay, so let's take a short break. When we come back, we will start to describe this 4 important concepts in some details. This is a bit different from your other courses in this department because I emphasize very much understanding of quantum physics and quantum mechanics. In particular, I would like to emphasize the interpretations in anything that you calculate and the relation to experiments, because physics is the experimental science. Okay, so we start from observations, and these observations are somewhat intuitive and in some other cases counterintuitive. So, and the quantum mechanics is really something counterintuitive, because we cannot directly observe the quantum phenomena in the ordinary condition, meaning room temperature. So those quantum phenomena occurs at very, very low temperature, at order of kelvins, which is minus 273 Celsius. And in room temperature, those quantum phenomena is smeared out. But these phenomena really exist, and they have been found and discovered in many breakthrough experiments that are summarized in Chapter 1, such as black body radiation and photoelectric effect and Compton scattering and electron diffraction and neutron diffraction and the Stern-Glock experiment for the spin and the hydrogen spectrum that could be described by the Bohr's theory. So these experiments are real, but they are not usually found in ordinary conditions. So many of these phenomena is really strange. Okay, they do not make any sense to our ordinary people. Okay, and the purpose of this course is to make sense out of this counterintuitive phenomena. Fortunately and unfortunately, those counterintuitive phenomena have huge impact in our daily lives and also in industry. For example, semiconductor chips, they take advantage of quantum phenomena, and MRI in a hospital, again, it takes advantage of this spin and nuclear spin, angular momentum, and so on. So many modern days technologies are derived and or are coming from the applications of quantum mechanics. So quantum mechanics is really important in both senses, in fundamental science and also in the aspect of applications. So you cannot avoid quantum mechanics. So everything is about quantum mechanics in modern technology. But fundamentally, this is a very, I just emphasize, counterintuitive subject, and which requires a deep understanding of everything that you learn. Okay? So questions are necessary, and confusion is good. You should get confused, otherwise you don't learn. Quantum mechanics, for example, the particle wave duality and Heisenberg uncertainty relations, they are really counterintuitive. Okay? So I know this pen, the momentum of this pen, and also the position of the pen. So what is the meaning of uncertainty? I know this for sure, 100% sure. What is the source of the error? You tell me. Well, you cannot observe these uncertainty relations in classical environment, such as these objects and a piece of paper and so on and so forth. You can only observe these uncertainty relations in the quantum regime, meaning a microscopic scale and a low temperature, atomic scale and low temperature. So that's the remark when you learned, and my encouragement, and also my recommendations. So let's start the first important concept, which is the particle wave duality, as I mentioned already. So I just like to highlight some important thought experiments and use a bit of mathematics. So this all comes from the Dirac thought experiments on this photoelectric effect. From photoelectric effect, we know that the photon or the light can actually excite electrons inside the material. For example, this material here, and kick some electron out of this material so that you could collect all these electrons kicked out by this photon on the other side of this material. So you can detect those, say, charge current and so on and so forth. You can design a circuit just like this original photoelectric experiments. But Dirac had a very interesting thought experiment. Suppose that I use a polarizer. The polarizer is kind of a technique that allows only certain, say, wavelengths or certain type of photon that could actually get through. For example, you could just screen the other, say this, you could actually put some polarizer, and which allows only this light wave, which is nothing but the electromagnetic wave, that the electric field parallel to that kind of a grid or the polarization directions that you set, and all the other electric field along the other directions cannot pass this polarizer, and which screen out most of the intensity of your light, but only allowed certain light that where this electric field shows a certain angle relative to some axis, and only electric fields of that wave, of the light wave, have that certain angle can pass through this polarizer. Okay, so suppose you put the polarizer in front of this photon source with an angle theta relative to the this horizontal axis, then only the light wave or electromagnetic wave which shows this particular angle could actually pass through this polarizer. And you know very well from this classical electrodynamics, you know that this intensity of this light wave, suppose the maximum intensity is actually I max, but once you put the polarizer in front of the light source, then the total intensity after the polarizer should be reduced. And by what amount? By cosine squared theta. So the reduced photon intensity is by a cosine squared theta compared to the maximum intensity without polarizer. So then you can imagine that on the other side of the screen, you get, again, the reduction intensity of your photoelectrons, right? Because there are not so many photons that hit this target, and therefore there's also a reduction of your photoelectrons numbers. And the total reduction of your photoelectrons is, again, that same amount that come from your photons or your light wave that is reduced by the polarizers. Okay, so you see from this polarization of the light, you directly conclude that there is a polarization or reduction of a photoelectron. Okay, but the light is a wave, right? What about the photoelectron? Of course, electrons are particles. So then you could have the following very strange conclusion that the electron's intensity after photoelectric effect is also reduced by that amount, and which immediately give you very strange the conclusion that only a fraction, which is cosine square theta, that amount of photons pass through the crystal, right? Because this polarizer is here, so only cosine square theta, that much photon can pass through the polarizer, and each of the photons that pass the polarizer could hit the target and kicks one electron out of this crystal, and so that you get total photoelectron reduction in intensity by the same amount, cosine square theta. But the question is, photon is a particle. As we mentioned, light wave is actually a quantum particle called photon, carrying quantum unit of energy, h times nu. So imagine this is a quantum version of this polarizer. So imagine there are a bunch of photons who want to pass through this polarizer, but we know the answer. The answer is there's a reduction cosine square theta. However, there are so many photons, and the question is which photon pass through this polarizer and which does not. So only a fraction of photons can pass through this crystal, but photon is a particle, so photon cannot split into pieces. This is a photon, a cartoon picture. So how can a photon split into, part of the photon? There's no part of photon. There's no 30% of photon. A photon is a photon. Either it passes through or it does not pass through. There's no percentage of photon. You see this counterintuitive consequence arises, so that is your challenge. So the photon either passes or not passes. But then there is a difficulty here, but there is no way of predicting whether any particular individual photon passes or not. In other words, we don't know which photon will pass and which will not. So that's the fundamental problem in quantum mechanics when we understand this particle wave duality. So we know the final answer, but we don't know which one passes and which one does not. So all we can say, or all we know, is that for n photons, their n times cosine square theta will pass. Okay? So, and this is the source of this probability interpretation. The necessity to understand this quantum phenomena is to introduce the probability. So for some reason, some photons will pass and some photons will not, but we don't know which one will pass and which one will not. All we can say is that there is that much reduction of photons that pass through the polarizer. As a result, the intensity of your detector that you detect the photoelectrons should be interpreted in terms of probability. And that probability, as we'll derive later, is actually proportional to the magnitude squared of your Schrödinger wave function. We will come back to this in just a moment, but here is a very simple thought experiment telling you that while we have a problem, there's no solutions, and the only solution is to introduce probability. Otherwise, we cannot make any progress. Then let's take a short break. When we come back, we will introduce another very interesting counterintuitive example, which is single particle interference. Again, which is based on some kind of phenomenological observation, and also some part of the thought experiments. Okay, so let's take a short break. So let's just look at another very strange counterintuitive experiments that a physicist called Taylor observed in, say, 19 Lec02. And what he found is that he used very, very low intensity of light and hit this needle. There's a very tiny hole in the middle of the needle. And surprisingly, he also observed this diffraction pattern. And from our conventional wisdom, we thought that you need to have enough intensity to give rise to such an interference pattern like you always do, in your textbooks. But even a very low intensity of light could actually give you such an interference pattern or photon diffraction. So this leads to a very interesting hypothesis that each photon may interfere itself. What does that mean? This is precisely this difficulty that we just mentioned a few minutes ago, that a photon cannot be split into pieces, right? So how can you say that each photon interferes itself? But of course, we don't know how many photons are there, even if this intensity of light is very low, but still there may be just very few photons around there. But imagine that you could turn down your intensity of photon even more until there's just only one photon passed through the needle, and in that extreme limit you can still see the interference pattern. Of course, this is not what Taylor observed, and he was not sure how many photons are there, but he found that even at very low intensity level, you can still see this interference pattern coming from the low intensity light, which leads to this very intriguing possibility that it is possible that each photon can interfere itself. This is really a fundamental, hypothesis in quantum mechanics, that each quantum particle, as I mentioned, shows double phases, right? And one of the phases is the wave nature. So if each quantum particle is a wave, and of course the wave could actually interfere itself. Okay, a particle cannot be split into pieces, but the wave could produce interference pattern. And this is the wave nature of a quantum particle. The earliest experiment that shows the wave nature of the quantum particle. But this is only the hypothesis back then, and we should analyze this in a more precise way. So classical physics tells you that if you have a wave, water wave or electromagnetic wave that pass through a double slit, and you're going to see this interference, right? So you know this pretty well. So you have, say, two electric fields at two different locations, slit 1 and slit 2, and these two electric fields will interfere, and as a result, these electric fields are vectors, and they could be superimposed, and at any particular points along the screen, and you could imagine that you have two electric fields that are superimposed at any given position, and they are vectors. So the intensity on the screen is actually proportional to the square of the electric field, right? The total electric field is a linear combination of these two electric fields, E1 and E2. And then you immediately see that there's interference going on, because if these two electric fields are vectors, and if you superimpose these two vectors together by linear algebra, you know that the square magnitude of these two vectors that are summed over is not equal to the square magnitude of E1 plus the square magnitude of the E2. And there's something else, and that something else causes this interference. There's a most important part of this square of this sum of these two electric fields, which is E1 dot E2. The dot product between E1 and E2 gives rise to this interference pattern. But the cosine theta is the theta between E1 and E2 vectors. Okay, so here comes another puzzle that you may or may not realize, right? So if this is a particle, so the difficulty arises if we apply the particle interpretation of this double slit experiments. So if they are particle, because we know they are particles, they are photons, right? Electromagnetic waves are photons. And we can also imagine this is a single electron and single photon, right? Just as indicated by Taylor experiments, that very low intensity, even at the single photon level, produces such an interference pattern. As a result, we can imagine that there's just one electron or one photon that passes through this double slit, and we can still have the interference pattern, but how do you understand this? This is the question. So how do you understand this? From the wave perspective, we understand this perfectly. If the electrons are wave and photons are also waves, and the wave can actually give rise to such an interference pattern, that's perfect fine. What about the particle nature? So if you insist that these electrons are particles and single photon is actually the particle, and we have a trouble. If they are particles, then we can ask the question, so if there's only slit 1 is open, then we should see that this intensity should be just proportional to E1 squared, and if only slit 2 is open, then the total intensity should be proportional to E2 squared. So this trouble is related to this Dirac thought experiment that's introduced, but in different contexts. But I will combine these two thought experiments together. So then this intensity leads to this probability interpretation that we just introduced earlier from Dirac thought experiment, come along here. Also happens here, because if only slit 1 is open, then the probability should be P1, which is proportional to E1 squared. And again, if only slit 2 is open, then the probability should be proportional to P2 and E2 squared. But now, if both slit 1 and 2 open, the probability is not the same as P1 plus P2. Okay, as we naively will imagine from this particle interpretation. So if those electrons and photons are particles, and we clearly show that there's no relation between these two slits, and as a result, we should naively expect that this, when two slits are open, single electron can either pass through the path slit 1 or slit 2, and as a result, the total intensity on the screen should be P1 plus P2, but no. As I mentioned, from wave interpretation, this E1 dot E2 makes a difference, makes interference pattern. As a result, is not equal to P1 plus P2. It's P1 plus P2 plus interference. So to resolve this, we should officially assume that each photon can interfere itself. Again, this is just assumption, but this assumption turns to be consistent with all these quantum mechanical experiments. Okay, we cannot prove or rigorously derive this assumption that each quantum particle interferes itself, but as I mentioned, the particle-wave duality is a fundamental concept in quantum mechanics. We don't know where this particle-wave duality comes from. So we have to admit that quantum mechanics is a mystery. Because why on earth that a quantum matter has dual faces, has a dual character? Or we can say that if we make such assumption and hypothesis, then we can make sense out of all these quantum mechanical results. Okay, so that's the logic. So we don't know why this dual character comes from, and what is the more fundamental principle behind this dual character, but we know the dual character is a foundation of quantum mechanics. Just like we don't know the more fundamental principle behind the gravity. We know gravity is here, but we don't know why the gravity is gravity. We don't know why the quantum matter behave a dual character, but we know they are. We know they do. Because if they don't have these dual characters, then we have a serious problem understanding everything. But once we accept their dual character, then everything follows. Okay, so this is something that you should know, that we don't know everything about quantum mechanics. We only know about the foundation of quantum mechanics and the fundamental assumption and postulates. But once we know these foundations, and everything just follows. And all this everything actually is consistent with all what we know from the experimental sides, because that's more important. Okay, so we should admit that each photon should interfere itself, as a wave character, and therefore at each position, by wave nature, we could associate a wave function of a single quantum particle, and the wave, say E1 or E2, should be interpreted as the probability amplitude of that quantum particle to exist or to be found at position 1 or position 2, and then we can make sense of all of this trouble. We can very clearly say that, well, one electron and one photon shows wave nature. As a result, we should attach a wave function to electron, a single electron, also a single photon. As a result, this wave tells you this probability amplitude that this electron or photon can be found. It's a probability distribution. It's not that we actually cut this electron into pieces. Okay? Instead, we should use a wave interpretation to interpret such electron diffraction, in the sense that each electron, each photon is associated with a wave function, and this wave function represents the probability distribution that we can find such a particle. As a result, we could attach all these different, say, wave function or electric field everywhere we like, and it is easy to understand that this matter wave interferes itself. There's no problem understanding this. So once we attach each quantum particle a wave, okay, so this wave describes, say, single electron and single photon and so on and so forth. Any single quantum particle should be attached to a wave function, and this wave function plays a similar role as electric field in your classical interference experiments, and later we will derive this equation, so-called Schrödinger equation, this matter wave should obey. So this E1 and E2 obeys linear equations, and also a large number of photons obey Maxwell equations. So then E1 plays the same role as electric field capital E1, and E2 plays a role as capital E2. As a result, if both slits are open, even at a single electron, single photon level, we understand that there is always interference because each electron, each photon interferes itself. So I believe that's something that you may not know about this when you take modern physics course. I would like to emphasize that this is the basic understanding or principles behind the quantum mechanics, that we should allow a single quantum particle to attach a wave. And in other words, when we understand this, say, wave properties of the quantum particle, and we should assume that the quantum particle is a wave. Okay, when we try to understand this particle characters, we should use the particle nature. Okay, so let's take a short break. When we come back, I will continue pushing this idea even deeper, and we will come back to this particle nature of this quantum matter and to understand this wave behaviors such as interference. So we will ask these questions. Yes, I know that if we just attach the single electron wave, and I could understand this interference pattern, but a particle is still a particle. What happened to the electrons when they hit on the screen? What happened? They are still particles, right? The photon is a photon, the photon is a particle. So what happened when those particles hit the screen? And then these interference could be, in what way that could we understand this interference pattern in the particle picture? We understand this wave properties, but they are in fact particles, right? So how can we still understand this wave interference pattern in terms of the particle nature? So that is more difficult challenge to your brain. You will get confused and puzzled by this back and forth particle and wave duality argument. But you should get confused. Okay, so let's take a short break. When we come back, we will comment on this particle interpretation of the wave behavior. 这门课的目的就是要刺激大家的思考啊，那所以这个逻辑跟推论还有理解是最重要的哦，那计算倒是其次了。所以呢，要动脑筋，要挑战自己的理解，挑战书本上告诉你的事情，然后也要挑战教授的论点。好，那你看你能不能挑战成功？所以量子力学是一个很有趣的学科。好，那你们在学完这门课之后，应该会感到有点困惑。那有点困惑是应该的，因为我们对量子力学的了解可能还没有100%，这也是为什么爱因斯坦说上帝不掷骰子的原因。哦，那我们可能必须要接受量子力学，它是不能说有缺陷，只是说好像少了什么，但是其实没有少什么。请各位在回去之后开始阅读第2章哈。那这部分会持续到下星期。Yes。
刚刚最后一段那个，跟那题安全器的那个部分，我不是很理解，为什么它就加起来，就是最后就变那个式就是。
好吧，也许我用中文解释好了哈。那是说 interference 那个吗？这个吗？
这个部分是想说我们要用波去解释我们前面遇到的那个问题。
是的。
然后最后面有说，就是有一个 probability 的 amplitude。
哦 ，OK， 是这个吗？
就是那个是在指哪里
？OK， 我刚才不是在这边有提到说这个是波的时候，我们可以把这些光波或者是水波，用某种电场的方式来理解吗？不是吗？你想你的古典物理或者是古典电磁学，光的干涉，你要怎么理解？不是就是2个向量的叠加来理解吗？对不对？那现在一个 single electron 或 single photon。我当然也可以用这种方式来理解啊，也就是说，它虽然是只有一个 electron 或是一个 photon， 可是它仍然会有某种电场、某种 wave function、某种波，这个波小1万就相当于是你的古典的干涉的电场大1万，小2就是一个 single electron 的 wave function， 就相当于是你这边的2电场的2。大跟小的差别就是小的就是 single electron single photon 的 wave， 那个不是电场，但是它扮演的角色好像是你光波古典的干涉的电场的角色一样，因为它都可以线性叠加，它同时可以造成干涉的现象。这样你能理解吗？就是这个符号不是等于的符号，这符号是表示相似类似的角色的符号。小1万跟小2代表的是波，物质波，不是电场。大1万跟大2表示是电场，古典的电磁波 给你的干涉的那个电场。小E1跟小E2是物质波，它不是电场，但是物质波跟电场扮演类似的角色。对，一个 electron 为什么会有电场？一个 photon 哪来的电场？或者是说，你用波来讲的话，你就是一个，你知道吗？水波也是一样嘛。你在这边有一个波，另外这边有另外一个波，它们是向量嘛，你可以叠加起来，对不对？一个 electron 你怎么可以把它切成两半？一半是在这边，一半在那边呢？主要的困难点是这个，但是我们的 solution 就是我们需要引进一个波的概念来解释粒子，因为粒子就是波，物质波，所以我们需要一个小一这样子的概念。它虽然不是真正的电场，但是它是物质波。那物质波可以造成干涉，就相当于水波造成干涉是一样的结果。虽然物理上是不一样的内涵，但是它扮演类似的角色。也就是说，小E1你要解释成为它会经过 slit 1的 probability 的 amplitude， 小E2是它会经过 E2 这个 slit 2的 probability amplitude。它同样是一个 single electron， 但是它有几率在这里，也有几率在那里。它不会被你切两半，但是它有的时候在这里被你找到，有时候在那里被你找到。这样你大概明白这个意思吗？它是 particle， 但是它同时是一个你不知道它什么时候在哪里的这个 particle。好，你回去再想一想，它是 particle， 它不可以被切两半，可是它在哪里你不知道。你把它们两个加起来，我就跟你讲啦，它们两个加起来不是E1的平方加E2的平方啊，它们两个不是没有关系的啊，它在哪里不知道，可是它们两个会干涉，不是独立的。如果它们两个是独立的话，那 intensity 就是两个平方和就好了。那就不是啊，你在屏幕上面看到的 intensity 并不是这两个平方和啊，而是我刚刚讲的这个平方和再加上某种干涉的效果啊。实际上看到的是这个有干涉的 pattern， 不是独立的 pattern。可是你要理解，你要从 single particle 怎么理解它又在这里出现，又在那里出现呢？我们必须要引进一个几率的概念。这几率的概念就由这个小E1跟小E2这样子的向量，就类似于电场的这种东西 ，wave function， 它其实不是完全是向量，但是它跟这个向量大E1跟大E2是很类似的概念。它是可以线性叠加的，它是可以有干涉的效果的，它不是独立的存在的这样子一个概念。它不能分两半，但是它可以有时候在这里，有时候在这里啊。这样你明白这个意思吗？ Okay, so we will come back to this in just a moment, but this is a very crucial point to understand this dual character. So let's just go to the particle interpretation of this wave interference. So let's just consider the particle interpretation of this electron diffraction. So take this double slit experiments again. So let's just discuss how we understand this interference. And for example, this may be, say, many electrons, or it could be a single electron, it doesn't matter. Let's assume that there are many electrons. As we mentioned, that each electron can interfere itself. As a result, we have to attach wave function to each electrons that come through slit 1 or slit 2, and this little E1 and E2 quantities are called the wave function, or the probability amplitude that this particle could be found near the slit 1 or slit 2. And these two quantities are not independent. They may interfere. As a result, they give you this interference pattern. But now, imagine there are so many electrons that come through these two slits, and as I mentioned, you don't know which electron come to which slit. You don't know beforehand. But the only thing that you know is that after some time, you will see this interference pattern, and intensity is proportional to this square magnitude of the sum of these two wave functions. Okay? So here comes the question, how come? So how do we understand from particle perspectives, meaning these electrons are really particles. They cannot be split into pieces, right? So, but we know that some electrons will go to slit 1 and another may go slit 2, but we don't know which one goes where. And what exactly happened when all these electrons showed up on the screen and give you such an interference pattern? So the question is, what is the intermediate stage? How do we understand from the beginning that there are many electrons go through this double slit, and at the very end you have this interference pattern. So what's going on in between? So what is going on? Which means that we like to follow this particle's trajectory and follow the particle's path and want to ask, how come some particles will hit in a particular position of the screen, but the other particles avoid a particular position of the screen? So how do they come about? They are particles. So we don't want to use the wave nature, but we like to follow the particles. So if we follow the particle, what happened? What happened if we follow the particle? After all, they are particles, right? So we want to know what's going on. We know the answer, but it's not enough. We need to know what is going on. So what is going on is understood in the following manner. So we need to know this measurement and the particle wave duality. So this is really important points that I think not many quantum mechanics courses will emphasize. But I think I should emphasize the connection between this particle wave duality and the real measurements. What you really measure, what you really see in the lab. So the particle nature are observed experimentally directly. Okay, so this is the most important statement here, that in experiments we directly observe the particle nature of the quantum system. Even though we don't really see this individual particle in our experiments, but this particle-like properties of quantum mechanics is actually directly observed experimentally, and the wave-like properties of quantum mechanics are only inferred in experiments. So the word inferred refers to the implications of this particle properties of quantum mechanics. In other words, the first nature of the quantum material is a particle nature, and the wave nature is only the secondary properties. It's a follow-up consequence of these quantum particles. It is a consequence of many quantum particles that come together and they obey some equations such as Schrödinger equations, and they show up as a collection of many quantum particles, and the wave behavior emerges only after you collect so many quantum particles individually. So let's just look at this double slit again. As I mentioned, a particle is the direct nature of a quantum matter, and the wave property is only the secondary or a follow-up or a consequence of this first nature. So let's just look at how these interference patterns come about. So as I mentioned, if you are experimentalist and you want to see what's going on, the best way is to take a snapshot. You take a Photoshop, right? You take a photo at instantaneous time, okay? And you take many, many photos at tiny little bit amount of distance between two times. Suppose that you have a very advanced camera that allows you to take a picture when the first electron hit the screen. And you can follow the second electron and the third electron and the fourth electron and so on. So if you take photos at any given time And even though this time difference is really tiny, suppose you could have such a time-resolved camera which allows you to see how does the interference pattern emerge. How do we see this interference pattern after a certain time? So in the beginning, there's no electron hitting on the screen, of course, but there must be the first electron to hit the screen, and the second, and so on and so forth. And how does this interference pattern emerge? From the beginning till the very end. So this is the question. So we should follow the electrons passing through the double slit and see why and how this interference pattern come about. So of course, at t equals 0, there's no electrons hitting on the screen, so you can only see the empty screen, right? But t equals t1, you see some electrons hit on the screen, but they are randomly distributed. So you see some random dots, only a few number of electrons hitting on the screen, and there's no interference pattern yet. You only see random dots. So that's what you expect if you take a really fast photo at a tiny little bit of time difference right after you start the experiments. But then you wait a few seconds or femtoseconds later, and at a later time, t2, you see more dots. So each dot represents each electron hitting on the screen. So, but then interference patterns gradually emerge. You see this bright region and this empty regions are separated, roughly speaking. So you can see more or less the little bit pattern start to form. So interference pattern start to form. And you wait until much later time, say t3 or t4, and you can very clearly see a clear interference pattern. Of course, there are some random dots here and there, but it doesn't matter because most of the electrons will hit only on the bright spots. And after the time t3, you see the interference pattern. Okay, so the question is, how come the electrons are so smart that they could hit this screen randomly at the beginning, and they somehow know where to hit. They collectively know where to hit. In order to produce this perfect interference pattern, those electrons, they seem to know each other. They are friends. Okay? They talk in advance before they pass in, they pass through the slits. So I will hit here, so you will hit there too. So let's go. It's like they have a conversation. But did they have a conversation? No. In the beginning, it doesn't seem that they have a talk before, so they just hit the screen randomly. But after many hits, many electrons hitting on the screen, so the interference pattern starts to show up. And that's the meaning of this direct and indirect observations. Okay? So the direct observation is the particle nature. So it is a particle nature that you actually see directly at the beginning. But of course, unfortunately, you don't have such a fancy camera which allows you to see these random dots, random electrons in on the screen in the beginning. Okay, so this is only our imagination, but this is not imagination. It's what happens if we really follow quantum mechanics. So the inferred property, the experiments, comes about when we have many such measurements or events. So this wave property in quantum mechanics is actually a statistical phenomena. So in other words, we can only statistically describe these behaviors in quantum mechanics when we take many measurements, meaning after many quantum mechanical events, we know their statistical behavior. And this is precisely what we expect and what happened in the real experiments, that we, initially we don't know where this electron will hit where on the screen, but after we wait longer enough time, we know the distributions of those intensities that most electrons will hit. So we know the high intensity regions, and we know the low intensity region. The high intensity region is the region where statistically most electron will hit. And the low intensity region is the region where statistically electrons will not hit. Those quantum mechanics in the form of the Schrödinger wave function describe precisely these statistical distributions. So each individual event cannot be predicted in quantum mechanics, but as a whole, as a many event collection, is a collection of many events, those statistical phenomena can be described by quantum mechanics. As a result, it doesn't matter if we know or if we do not know which electron come from where, but as a whole, as a full collection of those many events, we know statistically speaking, so those bright area is a high intensity area. It's an area where this most likely you can find electrons, and therefore they have a high probability, even though you don't know exactly this electron will hit where, but as a collection of many, many electrons, you know their statistical average behavior, or you know their statistical phenomena. On average, the high probable regions and low probable regions. And so this is the connection to this double slit experiment from particle perspective, and also important concept behind this particle wave duality from the experimental point of view. But I guess that should be enough for today. So let me just summarize. We have this particle wave duality, and we need to take this concept of the wave to describe a single electron diffraction or single photon interference. But when we contact these experiments, we should understand that these particles are still particles. Okay, they cannot be cut into pieces. However, collectively, they could behave in a statistical way that could be described by quantum mechanics. Namely, the wave nature is an indirect, a secondary phenomena or inferred phenomena, but we cannot directly monitor this electron pulse for all electrons because it's not possible. The only thing we can say is that statistically, after many such quantum events, they behave like the statistical average coming from Schrödinger equations. And here comes the concept of probability interpretation of the quantum mechanical experiments. Even though we don't know exactly what happened for each individual particle, but as a collection of many particles, we know statistically how they behave. So of course, all the quantum matter shows up these two phases, but we need to understand correctly what we can know and what we do not know. The quantum mechanics only describes what we can know. It cannot tell you what we cannot know. What we cannot know is forbidden by Heisenberg uncertainty relation. So that's the point. So let me stop here. I'll see you on next Monday. So try to read chapter 1 and chapter 2. I will see you on next Monday.